Hey folks, welcome back. This is Maria again. Okay, let's start with a brief review of what we've already learned in the last two videos. First is the essence behind all this, how to understand light. As I said, it's better to understand light as an electromagnetic wave for the scope of this presentation. What is it? Is really an oscillating electromagnetic field that propagates through a direction. That's light. And then we talk about the phenomenon. First of all, is the diffraction, really is wave superposition. And then we talk about scattering, which means the light needs to propagate through this matter, interact with the electron cloud, and the electron cloud creates an oscillating dipole. This oscillating dipole generates the scattered light. Again, is electromagnetic wave of the same frequency as the incident light. So that's scattering. And then we explain the theories. Fraunhofer diffraction explains diffraction. Rayleigh scattering explains scattering, but both of them have strict conditions, the size of the particle and the optical property of the particle, whether it's opaque and soft. And that's why me theory is the superstar that explains all this. It covers all size from molecules to galaxies and all optical properties, which is why you need to input the refractive index of the material. And Fraunhofer and Rayleigh scattering are really just the approximations of the Mee's complete solution. Okay, so the essence of Mie theory, I think, really is the angular dependence of the scattered light getting out of this particle. And we use this angular dependence in the technology which we still call laser diffraction, but it's not rigorously diffraction anymore. It's Mie scattering, and Mie scattering is really the angular dependence. So we use the angular dependence to measure particle size, and that's really what we say when we're talking about laser diffraction. Let's start today's video with our master sizer and the basic instrumentation inside it. So I've already mentioned it last time. What's inside, really the most important part is the detectors located at different angles so that we can detect the angular dependence of the scattered light. And that's what we use to back calculate the particle size. And first of all, this is the measurement cell. And yeah, this of course are the detectors. This is the focal plane detectors, which is the covers the forward scattering range. And this is where our red laser comes from. We've also got a blue laser because blue laser has a shorter wavelength, so it's better for small particle sizes. And for blue lasers, we didn't use a focal plane detector because when you're using blue lights, you really want to target on the smaller particles. And for smaller particles, the forward scattering is not important. Okay, just to let you know why it's not important, because it's the larger particle that has more forward scattering light. Okay, just a little bit more detail here. And let's continue with master sizer accessories. So we have a wet system. We call it hydro SV for measurement of a volume in this range. And this is the measurement volume, which is different from the sample volume, because in a lot of cases, you need to dilute the sample to be able to measure them. Yes, so that's the measurement volume. And we have a hydro MV, which measures a bigger volume of samples, and we have a lot more on our website. And then we've got the dry system, Aero S, and we have two kinds of feeders in terms of the energy to break the sample. So we have a high energy one that's like not better, but offers a higher energy in breaking the samples into like separated particles because some powders can like stick together. And we have another feeder that doesn't necessarily break the particles like with such a high energy. So that's the accessories of mastersizer. Okay, as I said, mastersizer is based on the technology called laser diffraction, which really is measures the angular dependence of the scattered light. And when it hits a point that the particle is small enough and it loses the angular dependence, meaning the scattered lights come out more isotropic or homogeneously, then what do we use? We couldn't rely on the angular dependence anymore. What we use is DLS, which is so smart. So let's start with DLS, which is the key point I want to talk about in this video. DLS is dynamic light scattering, and I had two lines linking it to Mie theory and Einstein-Stokes equation, but really 99% of DLS is Einstein-Stokes equation, or like the whole set of knowledge I'll talk about here, and only 1% links to Mie theory. And why is that when we're measuring using DLS, but we're still measuring a particle size that's large enough and has the angular dependence, we can utilize this angular dependence to better measure the particle size to have a better resolution, I'd say. So for example, in my PhD lab, we built our own DLS. We have an instant light. We have a detector that we can rotate to make it at any detection angle as we want. So we can really utilize the fact that different particle size has different scattered angle, and just by alternating this angle, you get a better resolution in terms of measuring the size. Yes, that's why I still have this line linking to the Mie theory. Maybe that's too confusing, right? Yeah. Okay, let's continue then. So that's Einstein-Stokes equation. So this is the Einstein-Stokes equation. I will start with Brownian motion. So Brownian motion, let's go back to Wikipedia page. So this little black particles, you can imagine it as a water molecule, as water molecules. Basically, it's the solvent. And the yellow particles is really what we're trying to measure. It's undergoing this random Brownian motion because of the collision with the water molecules or the solvent molecules. And when the particle is larger, it diffuses slowly and it diffuses around the original spot, I would say, and as compared to the smaller particles. The smaller particles, they diffuse faster, and soon enough, you've already forgotten the original spot where the diffusion starts. Okay, so that's Brownian motion and diffusion. So the diffusion coefficient of this particle is this equation. So Kb 6 pi are constants. T is the temperature, mu is the solvent viscosity, R is the size of the particle, the radius. And if we fix the temperature and we know the solvent viscosity, then by measuring the diffusion coefficient, like how fast and slow the particle diffuses, we measure the particle size. Just to add one comment here to make me look smarter. If we know the particle size and we fix the temperature by measuring the diffusion coefficient, we measure the solvent viscosity, and this is called microrheology. Okay, so how do we measure the diffusion coefficient then? Because that's really the key here, right? That's the measurement principle we're getting into. And it may seems to be complicated, but just bear with me. So we measure how fast and slow the particle diffuses by measuring the intensity fluctuation of the scatter light. So the particles are too small. How can you see like its diffusion? We see it by seeing the scattered light and how the scattered light fluctuate. So a small particle like diffuse quickly, and there's lots of going on in the region that a laser hit, and the scattered light fluctuates more crazier, will be a better word. And the large particle, the scattered light fluctuation is smoother. I'm using weird words. So from the fluctuation of the scattered light, we calculate the autocorrelation function. And feel free to learn more about the autocorrelation function. But for the scope of this presentation, we just treat it as math. And computer handles all math. From the scattered light intensity, this I here means intensity, we calculate this autocorrelation function, and we by regression of this autocorrelation function, we can calculate this parameter d here, which is the diffusion coefficient. And then from this diffusion coefficient, we calculate its radius by Einstein-Stokes equation. Okay, so it's really, we're measuring the diffusion of the particles by measuring the fluctuation of the scattered light and then autocorrelation function. Cool. Then that's DLS, dynamic light scattering. The take-home point here is dynamic light scattering measures particle size based on the diffusion of the particle inside the solution. It's completely different from laser diffraction, which calculate the particle size based on the angular dependence of the scattered light. Okay, that's the end of my presentation. I hope this map make more sense to you, and any questions, please let me know. Okay, thanks for watching. Bye bye. See you next time.